My name is Philip Tissot, and I am one of the co-PIs for the AI2ES AI Institute. In this video, we will share the research conducted by AI2ES at Texas A&M University Corpus Christi with Del Mar College. We have put together 3 sections, each focusing on one of our main research projects. The sections start with the PhD student who's leading the research, and then continues with MS and undergraduate students who support the research and help make our models accessible to stakeholders.
Hi everyone, my name is Miranda White, and I'm a Coastal Marine System Science PhD student at Texas A&M University, Corpus Christi, and also a part of the NSF AI Institute. My research focuses on communicating variability, uncertainty, and trustworthiness of an AI ensemble model that predicts cold water temperatures within the Laguna Madre. Given the climatic conditions of the area, the lagoon system is sometimes susceptible to lower water temperatures and freezing air temperatures when cold fronts pass through the coastal system. Because of these conditions, the lagoon itself can cool down very rapidly and can serve as a trap, causing them to become cold-stunned and susceptible to being damaged or killed by large barges or even smaller recreational boats. These conditions give insufficient time for sea turtles to move and reach warmer areas. These green sea turtles are a prized ecological possession within the local coastal bend community. The TCRC was formed with the goal of improving conservation and recovery efforts of cold-stunned sea turtles and minimizing fish kills during these rare cold events. TMUCC AI researchers have developed an AI model that predicts water temperatures in the Laguna Madre, and the predictions have allowed coastal stakeholders to take measures within their own hands to try to minimize the impact of these rare events by organizing volunteers and partners and or by interrupting navigation when water temperatures drop below the critical threshold.
Hi, I'm Christian Duff. I'm an undergrad here at TAMU-CC, computer science major. I'm here with my research partner.
I'm Jarrett Woodall. I'm an undergraduate researcher from Heidelberg University in Ohio, and I'm also a computer science major. And we're going to be talking to you guys about our efforts for turtle conservation with using AI predicting models. So with our project, we are basically using AI to predict cold stunning events, which is when water temperatures dip below a certain degree, I think around 8 degrees Celsius. And our model is to help first responders be able to predict when these events are going to occur and be able to coordinate better rescue events in the event these cold stunning events happen. And right now we have two models that we've been working on. One is a shallow neural network that is a little more simpler, but it is effective. And we also have a LSTM model that we have been ironing out the kinks. And so far it's looking like it is beating the previous model very, very well.
So within our models, the input parameters we're using to help predict water temperature is previous water temperature, previous air temperature, and predicted air temperature. And some of the things we're looking at potentially using in the future to help better optimize our model could be solar radiation, taking that into account, humidity, barometric pressure, things like that nature.
Hi, I'm Hector Marrero, an undergraduate research assistant here at TAMU-CC, studying under Professor Tissot. Today, I'm going to demonstrate our new interactive TV that we use to display our models. Here on the top right, we have our water level graph for Aransas Pass. As you can see, it's working. We can interact with it. The top left is the one that we're going to focus on. This is our water temperature model for the Laguna Madre, which is the bay for the sea turtles. We are currently seeing our live predictions. This red now line is our current date and time. So we can use to monitor our future predictions on the right and our past performance here on the left compared to the actual measurements. This is very important because we have this dashed line here for the water threshold if the temperature gets too low. Right now, we're pretty safe now.
Hello everyone, my name is Marina Vicens Miquel and I am a PhD student at Texas A&M University Corpus Christi. Here in Corpus Christi we're working in coastal AI, so my main project and the goal for my dissertation is to predict coastal inundation. In order to accomplish that, we decided to divide the problem in 3 steps. The first step is that we need to create a general model to detect what is the shoreline. And it's necessary to create a model because we need a long time series of data, so it would take a lot of time to manually label all this data, so we need a method to do that. The first idea was to use UAV imagery to do that. The second goal is to predict water level, and finally combining this with other variables and wave information, we will be able to predict inundation. So that's the goal that we have right now. So in order to predict the wet dry shoreline, we decided to use an edge detection model. The goal was to test it in multiple locations, so we used data from 9 UAV flights, both in Texas and Florida. Since the data was very different, it was very hard to generalize. So for this reason, we decided to use as an input CLI. CLI stands for a contrastive, limited, adaptive histogram equalization. And what it does is it equalizes all the images from different locations while at the same time increases the constant. Also, we decided to make some modification to the AGD architecture because it had problems to generalize, but if we use CLI, if we use the dilation rate that we had in different convolutional layers, and if we use auto-regularization, we were able to create a model that was able to predict the wet dry shoreline. In addition, we were able to predict the height of the shoreline. So here we have some of the examples of the data. One thing that is interesting in that in Texas beaches we have cars, and cars are edges that are in the beach, so sometimes it can be difficult for the model to be able to predict the edge while you have a car. But as we can see in the top image, our model is doing a good job. Also, if you look at both images, you can see that they are different. The light conditions are quite different. And in the second image, it's pretty hard to see the shoreline just because there are multiple edges, so that's a challenge. Here we were able to georeference all the predicted images. The red line is the label line. So as you can see here, our prediction model, for some reason it predicts some extra pixels, so our shoreline is a little bit wider. But overall, we're able to successfully predict the shoreline. And note that this area was in fish pass and it was used as a test as an arbitrary. So in this particular case, we were testing our model in one location while it was trained in 8 different other locations in both Texas and Florida. So for the next step, what we really need is to be able to create a model that it allows us to create a time series. That's why we decided to install a camera in Oracle Cowell Pier. So we have a team that is going to install the cameras where in that building, so we can get a time series of a couple months where the shoreline is. Also, we have a team that is working in generating a DTM model, so we could have access to the shoreline elevation.
My name is Matthew Castle. I'm an undergraduate researcher for AI2ES, and I'm studying a Bachelor's of Computer Science.
Hi, my name is José Pilates Congo. I'm a PhD student in the Geospatial Computer Science program.
We're studying the beach out at Horace Caldwell Pier for the Coastal Inundation Project, and my job is to help build a camera array that we're putting out there so we can take a time series of images of the beach. We're putting out 3D stereo cameras and regular cameras. One of the regular cameras is even going to be a surf cam that will allow the community to check the conditions of the beach.
And I'm working specifically with one of the cameras Matthew's putting up, the Z2i stereo camera, and we're using that to produce point clouds and digital elevation models, which are going to be fed into the AI to predict inundation and shoreline change.
Hi, my name's Katie Colburn. I'm an undergraduate research assistant at the Conrad Blücher Institute at TAMU-CC, and I'm majoring in kinesiology.
And I'm Savannah Stevenson. I'm also a research assistant at the Conrad Blücher Institute at TAMU-CC, and I'm majoring in computer science. Right now, Katie and I are both working on the Coastal Inundation Project. More specifically, we're part of the surveys that we're conducting at a beach in Port Aransas. And so what we're doing is we're taking elevation shots on the beach according to a grid that Judy Millen laid out. And so we find the point and the satellites are like, oh, you found it. And then we take the elevation shot. And that's helping us collect data for Katie's.
Yes, so after we get the elevation shots, we overlay it with aerial images and pictures from a camera that we're putting up on a local pier. And I go into ArcGIS Pro when it's North Mosaic and I delineate the shoreline. And so right here you can see this is the original image, this is my delineation, and then over there in the corner is the AI's prediction after being trained with my delineation. After enough time and enough images, the goal of the project is for the AI to successfully delineate the shoreline and predict coastal inundation. We're doing things at Port Aransas so that we can get more weather conditions and the AI can be trained in a variety of settings.
My name is Judy Millian. I'm a student at TAMUCC in the master's program in geospatial systems engineering. And I will be showing you guys basically what I've been doing at the Horace Caldwell Pier. And we have been observing the wet-dry line and also doing a surveying based on a 10 by 10 grid. So this is a grid of the site area near the Horace Caldwell Pier. And what you're looking at is the wet-dry line shot on certain dates. And so far we've been doing this bi-weekly. And again, the cyan line is the wet-dry lines based on the dates that they were shot. And on this screen, this is the DEM or digital elevation model of the exact site as well. And again, we're using a 10 by 10 grid, so it is a lot more dense, and we're able to get as much elevations as possible.
My name is Bethel Schroeder Jr. I'm a computer science major at Texas A&M University, Corpus Christi, with a minor in atmospheric science. I'm also a graduate of Del Mar College. Today I'll be going over my AI2ES research project on coastal inundation, as well as my experience so far as an NRL NREP intern. So starting off, I've been working as an AI2ES undergraduate research assistant for over a year and a half now. My focus has been on acquiring real-time data for predicting coastal inundation and using that data to create interactive web tools for stakeholders to utilize. One example is this web tool on the bottom for Ingleside, Texas. The black lines are for the water level measurements, the blue lines are for the water level predictions or tidal water levels, and the green line is a persistence model that we implement which factors in the wind and the waves into these predictions. And the red line, if these measurement predictions cross the red line, then that means that there's a risk for flooding, and we can tell the stakeholders that they should prepare for that.
Hi, I'm Ashley Marinas. I am a junior at Texas A&M Corpus Christi. I'm a transfer student from Del Mar College, and my major is physics.
And I'm Dante Ramirez, a computer science student at Texas Tech University, here under the REU program, working with Dr. Tassel. And me and Ashley are both working on the coastal inundation project, specifically water level predictions.
So the end goal is to predict water levels to save lives, also to protect the infrastructure along the coast, and to help marine navigation.
And currently, water level predictions aren't accurate enough, so me and Ashley are working to see the performance of the shallow neural network as well as the long short-term memory architecture, specifically on Bob Hall Pier, so we can see which architecture to move forward with the coastal inundation project.
So for future work, we're hoping to use our architecture at different stations along the Texas coast and measure its performance.
I'm Evan Krell, a student in the Geospatial Computer Science PhD program at Texas A&M University, Corpus Christi. Here I am presenting our AI2ES work related to forecasting coastal fog using deep learning. The port of Corpus Christi is one of the largest in the nation. It experiences a large economic impact from the fog. We are working with Waylon Collins from the National Weather Service to develop a fog forecasting model called FogNet to meet the needs of local stakeholders, both marine and air. Accurate fog predictions could be used to strategically operate vehicles to increase both safety and efficiency. Suppose it is known that there will be significant fog in 6 hours. The ship could slow down, saving fuel, and timing it just right to arrive after the fog has dissipated. On the top left, you can see a graphic of the FogNet input features. This is a raster with a 32 by 32 spatial grid for each mid-ocean variable and up to 384 channels for 24-hour forecasts. We developed a 3D convolutional neural network where spatial convolution occurs along the spatial and channel-wise data elements to learn 3D features. This is useful when the adjacency between channels has meaningful information. With FogNet, adjacent bands may be the same variable at different time steps or at different pressure levels. So we use 3D convolution to learn spatiotemporal features associated with fog. Part of the challenge is the high dataset imbalance. I'm currently speaking from Monterey, California, where coastal fog is a near daily occurrence. But for our study region, we have relatively few fog cases in the training data, which is a machine learning challenge. Much of the complexity of the FogNet architecture, shown at top right, is due to this imbalanced dataset problem. The bottom right figure shows the FogNet model with 3D convolution compared to 2D CNNs, where the conventional CNNs struggled to reliably learn prediction strategies. Part of trustworthy AI is understanding how the model makes its decisions. Do these align with domain expertise? We applied variants of Shapley-based explainable AI techniques. Based on game theory, these methods calculate the contribution of each feature toward the model's decision. On the right, darker red means that the feature at that spatial location contributed toward the decision. So for a hit case, red regions lead the model toward predicting fog, while blue mean that the region was leading the model output away, that is, toward not having fog. The plot on the left is the SHAP values for the 7 channels in each outcome. The green X corresponds to the airport at Mustang Island, the location of the fog-not fog target class. We are working with meteorologist Waylon Collins to analyze these results. Preliminary findings suggest that the model is focusing mostly on the area immediately around the airport, where we initially expected to see more influence from the offshore winds. Based on this, we are now working on a new architecture completely focused on data near the target to compare performance. Maybe we can build a more efficient model that is easier to train and using a less complex input. We expect our continued explainable AI analysis to provide further model insights to help us strategize toward model improvements.
I'm Brian Colburn, mathematics major and undergraduate research assistant at Texas A&M University of Corpus Christi. I'm developing the simpler fog prediction model that Evan Krell mentioned in his presentation. The model uses predictions from NOAA's high-resolution rapid refresh model as inputs and uses visibility observations from METAR stations as target values. Currently, the model is focused on Mustang Island as FogNet was trained and tested at that location. However, it uses training data from across the coast of Texas, and we are planning on expanding the model all along the Gulf of Mexico. The model is a variational autoencoder. It takes in all prediction values from the 4 HER grid points surrounding the location and compresses them down to a bottleneck containing 1 to 20 neurons. From there, it attempts to reconstruct the input values as well as classify whether visibility for those conditions would be below 1600 meters or not. The model is trained with the Adam W algorithm and uses a root mean square error loss function for the decoder and a weighted cross-entropy loss for the classifier. The weight of the low visibility cases varies from 1 to 80 times that of the standard non-low visibility cases. And the hyperparameters are tuned using the Optina library, with the goal of maximizing the model's POD and minimizing the model's FAR. In the box here, you can see an example of one model that takes in 4,300 inputs, compresses them down to 3 neurons, and then reconstructs the models from there. There were 4 different strategies used to train the model. From that, we developed 4 different ensembles. The ensembles were evaluated by taking the top 5 highest scoring models by Pierce skill score and constructing an ensemble from there. Here we can see the results of the new model. Ensembles were constructed from 4 different training cases and evaluated against NOAA's href model and FogNet. Cases 2 and 3 performed better on POD and PSS metrics. However, FogNet outperformed all cases on CSI, RSS, and most other metrics. The 2 cases trained on multiple locations, however, outperformed the cases that were trained on only 1 location, which is encouraging as it shows the models can generalize spatially.
Each stakeholder has different needs, concerns, and values. Model systems such as ours need to fit those needs and align with those values in order for our models to be trustworthy. As researchers working with operational predictive tools for the betterment of the natural and human community, our communication goals should be focused around conveying scientific information in a way that considers multiple target groups of people and settings that would help to support efficient research uptake and decision-making processes and practices. Addressing and improving deficiencies in the dissemination of research-based knowledge is imperative to the future of connecting and applying scientific research into other fields and policy. By carefully planning and analyzing the audience with whom scientists discuss their research with, scientists may expand and visualize their research in contexts not initially considered or thoroughly explored. By including key stakeholders in scientific discussions, it would encourage participants to make informed choices on science-based issues and increase the overall acceptance of scientific and technological innovation.